me press the record button. Yeah. Good afternoon, everyone. So let's start today's seminar. The seminar speaker is Professor Gerrit Schierholz from DESY, and here we're going to talk about a very interesting topic, the dynamical solution of the strong CP problem. Professor, please start.
Okay. Well, thank you very much. And I'm pleased to give the seminar. Thank you very much for the invitation. And so what I will present you is a dynamical solution of the strong CP problem. And this is work I have done together with Yoshifumi Nakamura from Riken in Kobe. Now, the outline of my talk is the following. I mean, I give an introduction or motivation, for doing this work. And then I first introduce you to the gradient flow, because, the strong CP problem, is a nonperturbative problem involving the topological structure of QCD. And in order to solve this, you have to isolate, the relevant non-perturbative modes and follow this up to the hadronic scale, like you do in confinement. And in order to do so, you need some kind of a renormalization group transformation, and the gradient flow is just that. And before I come to the phase structure, what I will show you, is that QCD in the presence of a theta term, has a very non-trivial phase structure. Before I apply the gradient flow to the phase structure, I will confront it with the issue of confinement and phenomenology as a kind of a test, and also in preparation of what I will talk about later on. And then, when you talk about the strong CP problem, then what comes to your mind is another solution, like the axion, and also the search for CP violation. And that is usually done, by searching for a non-trivial electric dipole moment of the neutron. And then I will finish with some conclusions. Now, let me start with a kind of an introduction. And as you all know, QCD describes, the strong interaction very well. From very small distances, described by perturbation theory, to hadronic scales, where confinement comes relevant. But it has a problem. And the problem is the following. The action allows for a CP violating term. It has the action decomposes in two parts. The usual QCD action and what is called a theta term. And this theta term is just, if you write, it's just a phase, so to speak. It is, in the Euclidean, it is imaginary. It has an angle, it's called the vacuum angle, and the topological charge. And topological charge is the integral over FF dual. And this is an integer. So this is basically only a phase, and this phase, this vacuum angle theta, can assume values between minus pi and plus pi. And this piece is, of course, CP violating, and a non-vanishing value of theta would result in electric dipole moment of the neutron, for instance, for the proton also. And the current experimental limit, is very tiny. If you write this dipole moment in terms of two charges separated by a distance, and you blow the neutron up to the size of the Earth, then this is a distance. This corresponds to a distance of a micron. You can imagine, how small this, how severe this bound is, and how small the electric dipole moment must be in order to satisfy this bound, if there is one at all. And anyway, what this suggests is, I mean, that this angle theta, or this theta term altogether, I mean, is anomalously small. And this feature is called the strong CP problem. And this is, besides QCD, is one of the millennium problems. And it is unsolved so far. Now, I mean, the prevailing paradigm is that QCD is in a single confinement phase. I mean, that's what it's always assumed. And for instance, I mean, if you take the Patrick-Quinn solution, I mean, the axion solution, then, I mean, this has a kind of a shift symmetry. And you can, by this kind of a shift symmetry, you can remove this angle, practically shift it to 0 or shift it somewhere else. That, of course, assumes, I mean, that you don't do any harm to the vacuum when you apply this kind of Patrick-Quinn not anomalous chiral transformation. But that is not quite correct. It is known from the Messer-Schwinger model, I mean, that a theta term may change the phase of the system. I mean, there is a very well-known paper or review by Coleman where you can read about this. Then Kellen-Deschner Gross, I mean, already in the end 70s have claimed that a similar phenomenon occurs at QCD, namely that the color fields which are produced by quarks and gluons will be screened by instantons for any vacuum angle different from 0. And I mean, this has, well, I mean, has never been really taken seriously, which is really surprising. Now, the Kellen-Deschner Gross have been very vague, I mean, on this, in their claim, but I will come back to this and you will see that this is basically true. Toft has been much more specific, and he has argued that the relevant degrees of freedom which are responsible for confinement are color magnetic monopoles, and they come about by partial gauge fixing to the maximal abelian, leaving only the maximal abelian gauge of SU3, which is U1 cross U1 unbroken, and the monopoles come about as a singularity of the gauge condition. But that aside, in this picture, I mean, confinement occurs when the monopoles condense in the vacuum. And that has been shown, I mean, for the first time, I mean, in the 80s, I mean, by these authors here, including myself. And by analogy to superconductivity. And superconductivity, the Cooper pairs condense, but in this case, I mean, the monopoles condense, and so the color electric charges are confined. And then, I mean, due to the joint presence of gluons and monopoles, I mean, you can imagine a very rich phase structure, and that has been worked out by Toft, I mean, to some extent in his seminal paper, which is called Topology of the Gauge Condition. Now, what does it mean? I mean, what I've shown here is the root lattice at 0 vacuum angle. I mean, you have the following charges. You have 1 unit charge of the gluon. You have half a unit color electric charge of the quark, and you have 1 unit of Dirac magnetic moment of the monopole. Now, if you go to vacuum angle theta different from 0, then according to Witten, the monopole gets a color electric charge. And then you can imagine, I mean, when the system has accumulated enough color electric charge, then this color electric charge can, of course, screen, I mean, the color electric charge of the gluon and the quarks. And this is very similar to QCD with dynamical fermions, with dynamical quarks. I mean, where, for instance, a quark will screen itself. So in this talk, I will investigate the long distance properties of the theory in the presence of the theta term, and show you that CP is naturally conserved in the confining phase of the theory. And okay. So the basic tool I'm using is the gradient flow. And what does the gradient flow do? The gradient flow it does exactly what you want. I mean, I should say, right. I mean, it involves a passage. I mean, from the it's this kind of a renormalization group transformation. And as I said in the beginning, I mean, what you want in order to reveal, I mean, the macroscopic properties of the theory, one is faced with a multi-scale problem, and one has to isolate the long distance mode. And that means, I mean, you have to sort of integrate out the ultraviolet fluctuations in order to make the long distance mode visible. And that is what the what the gradient flow does. And it is a kind of a renormalization group transformation. So I've written down here the relevant equation, and what the gradient flow does. I mean, you start with the gauge field, I mean, at flow time 0. And what the gradient flow does, I mean, it involves the gauge field along the gradient of the action, and that's why the name the gradient flow comes from, to larger flow times, and by this diffusion equation. And this defines the scale, and the scale, I mean, what you can translate, I mean, this flow time t, I mean, into a scale, and there's some arbitrariness, I mean, in this scale, but that doesn't matter for us for the moment. And while this is a very technical part of the talk, and I mean, time doesn't permit me, I mean, to go into the detail, but the only thing I want want you to know is, I mean, as I said already, I mean, the gradient flow does exactly what you want. I mean, it isolates, I mean, with increasing flow time, it isolates the long distance non-perturbative configurations. And when, for instance, at large flow time, I mean, it's like in the renormalization group transformation. I mean, when you go to larger and larger flow times and smaller scales, then I mean, all the basically all the gauge fields are integrated out and put into the bare parameters, and you can already read off from the bare parameters a lot of the features of the theory, and I will come back to that. So what you should take home with is that the that the gradient flow, first of all, it's a tool for scale setting. This means, I mean, you can you can look at the theory at different scales. I mean, by employing this diffusion equation, and moreover, I mean, it has the features of the renormalization group in as much as it is an infinitesimal realization of the coarse-graining step of a momentum space renormalization group transformation. And as such, I mean, it keeps of course a long distant physics unchanged. I mean, that is an important point. I mean, if you want to read, I mean, about all these, I mean, I have been very diffuse about this part. I mean, as I said, I mean, this would be a seminar by itself. I mean, to really explain, I mean, this renormalization group transformation. I mean, the renormalization group, I mean, this has been with lattice gauge theory, I mean, for many years. I mean, people try to block the lattice and making into a coarser lattice and mapping one lattice onto the other, but that has not been very successful. But now we have a tool, I mean, which fulfills all the properties of the renormalization group transformation, and we can by varying the scale, I mean, we can go from the perturbative asymptotically free the limit, I mean, of the theory, I mean, to the confining limit, and you will see, I mean, how this works. And there has been a particular work by Suzuki from Japan, and he has worked out, I mean, that this gradient flow is really a kind of renormalization group transformation. I mean, if you have questions, I mean, to this part, I mean, please ask them now, and if not, I mean, I will go on. Of course, I mean, when you change the scale, I mean, the force laws underlying the physics, I mean, will change with respect to the scale, and varying the scale, I mean, the Green's function and couplings and so on will satisfy standard renormalization group equations. Among them is the strong coupling constant, which will, or the running coupling constant, which will play an important role in what I continue to say. And the expectation value of the energy density, I mean, at flow time t, I mean, that has a perturbative expansion, I mean, which is written here in terms of the running coupling constant at scale mu in the MS bar scheme, and that can be transferred to any other scheme, and this defines running coupling in the gradient flow scheme, and the lambda parameter, I mean, from one scheme to the other, I mean, is basically given by this parameter here, and it is known in the literature. Now I come to the lattice, and so what I will look at is the pure Young-Mills theory without any quarks at the moment. And my attitude is, I mean, if the strong CP problem is resolved in the Young-Mills theory, this means QCD without quarks, then it is expected to be resolved in QCD as well. And while I could in principle skip the detail, but I'll give, because as you said at the beginning, I'm not very familiar with the lattice. Let me spend a few minutes on that. I mean, first of all, you have to design an action, I mean, on the lattice. And on the lattice, I mean, the gauge fields, they live on links between lattice sides. And by taking the product of these links around a plaquette, which is called a plaquette, this is written here, and expanding this, I mean, in powers of the lattice spacing A, then you can see that this is basically giving you the action plus corrections, which are of some power of the lattice spacing. Another quantity which will be important later on, I mean, is what is called the Polyakov loop, which is just the product of these links, I mean, across the lattice, and lattice is periodic. So this point here is attached to this point, and so the Polyakov loop is just the product of these links around along the time direction of the lattice. Okay, And the calculation are done at some coupling, and which refers to lattice spacing of 0.08 Fermi, which is considered to be relatively small by present standards. Yeah. And the calculation is a very high statistic calculation. I mean, it's done with over 5,000 configurations and on 3 different lattices in order to really rule out any finite volume effects. So as I said, I mean, if this gradient flow is a renormalization group transformation, then I mean the physical quantity should be independent of the renormalization group scales. And I give you 2 examples. One is the topological susceptibility, which is just the square of the topological charge, which takes integer values, and subtracted is a vacuum value. This means, I mean, squared divided by the volume. This is shown by the red points here. You can see up to very large flow time, and that is really independent of the flow time. Another one is the Polyakov loop susceptibility. The Polyakov loop describes static quark. Well, we don't have any quarks, but it mimics a static quark around the lattice. And the Polyakov loop susceptibility describes the interaction between these static quarks. Usually, this is at large distances. This is usually giving you the string tension. Yeah, I mean, because I mean, if you have confining forces and you want to try to take these static quarks apart, I mean, then you feel the confining forces, and it should be proportional to the lattice spacing. But the gradient flow has many other salient features. One is, for instance, that operators are automatically renormalized. As you know, probably from QCD, when you do any calculation, then operators develop a anomalous dimension, and you have to renormalize these operators at particular scale. And what I show you here is the quark mass as a function of flow time, and these are the bare quark masses without any renormalization. And at flow time 0, I mean, usually you have to renormalize them. I mean, in QCD. I mean, this is QCD now with masses, quark masses, and this is done here. But then, I mean, if you apply the gradient flow, you can see, I mean, already at very small flow time, I mean, the bare quark masses agree with the renormalized quark masses here, and this is really a very interesting feature of the gradient flow. And well, it will be used. I mean, it helps also other calculation like calculation of matrix elements and so on and so forth. Now, as I said already, I mean, before coming to the theta term and the phases of the theory in terms of theta, I want to confront the gradient flow with phenomenology and with confinement, and also in particular with confinement in preparation for what I want to say later. So let us look first at the gradient flow coupling. As the scale goes to 0 or the flow time goes to infinity. And what I've shown here is the gradient flow coupling, running coupling over the Pion mass. And what you see is that this lies on a straight line. Yeah, I mean, as a function of flow time or as a function of 1 over u squared. And from this linear behavior, you can compute the beta function, and because it is linear in 1 over in t, or t was proportional to 1 over mu squared, then if you take the logarithmic derivative, then you get for in this range, for large for non-vanishing t values, you get the beta function, which is 2 times the alpha. And if you want to compute the mu dependence of the running alpha, it is usually given by this renormalization group equation, and it involves the beta function. And once you know the beta function and you're only interested in solving this equation for very small mu, then what the solution you find is that this gradient flow coupling is just the lambda squared in the gradient flow scheme over mu squared. Yeah, and mu squared was basically t, and so this describes that this really runs like proportional to t. Now the gradient flow scheme is not very convenient. To compare it with phenomenology, and the preferred scheme, in the Young-Mills theory, is the V scheme, the potential scheme, and it is in perturbation theory. And in the potential in momentum space is just given in terms of this running coupling in the V scheme is given by this equation here. And once you take this equation for one scheme and divide it by the similar equation for another scheme, for the other scheme, you get this relation. And again, you can compute the relation between these lambda parameters in perturbation theory, which is all very well known, and you can solve it. And what you find is that the beta function has the same structure in the potential scheme, and you get the running coupling to have the same form, only that in the potential scheme, only that the lambda parameter is changed. And okay, and so far you can even go a step further from a fit of this running coupling, and with this relation, you can compute, lambda in any other scheme. Yeah, we know, for instance, the ratio of the lambda of the V scheme to the MS bar scheme is given here, and from the MS bar scheme to the gradient flow scheme. And if you put it together, what you find is that the lambda parameter in the MS bar scheme coming from this fit is this value here. And in the literature, from a completely different calculation, you find for this lambda parameter a value which agrees very well with this number here. And this is, of course, a dimensional quantity, and I took some particular t value here, which is just a convention, in order to make it dimensionless, but this is the same in both cases. So this has the gradient, this is very important, that the gradient flow is that you have trust, in this gradient flow. Yeah, so it should, it is a completely different method, but it should give you the same answer, as other methods, and that is the first test. You could have, or I could have already looked at the, given you the number for the topological accessibility, which is given here, and this can also be computed in a completely different way. Not using the gradient flow, and that also agrees very well with the number with the numbers here. Okay, so now as said,
hello.
Yeah,
I have one question about this slide. So you have two different ways of the estimating lambda ms bar. And my question is, what kind of experimental input you use to fix this lambda ms bar in this case?
Well, I don't know
It's
any
experimental data.
No, I don't need any experimental data. Yeah, this is this one here is, well, it is in the Young-Mills theory, which has no quarks in it, but it is from a lattice calculation. Yeah, I mean, this number here is not experimental. It is from a lattice calculation, and but in a completely different way. Yeah, I mean, you can compute. There are many ways. I mean, of compute the running coupling and how. But this is from a calculation at large Q squared, yeah, at large or large mu. I mean, and my calculation is from very small mu, and this is to say, I mean, that these two numbers completely agree. Yeah. Now, as I said, I mean, what will be important for my later conclusions is to confront it with confinement. Yeah, I mean, what I mentioned already. I mean that that CP is in the introduction, that CP is conserved in the confining phase of the vacuum. So you have to make contact to confinement, and you will see why. Yeah. So this is what I'm doing right now here, and so the linear growth, I mean, of the running coupling in this V scheme with 1 over mu squared. I mean, this is commonly dubbed infrared slavery. Yeah, and this so if you compute the static quark anti-quark potential, then I mean for very small mu, then you can describe it by the exchange of a dressed gluon with the running coupling here. Yeah, I mean, this is very old. This is very old story. I mean, this is basically goes back to Richardson potential, and okay, but in the old days, I mean, people have assumed, I mean, in order to understand, I mean, how confinement comes about, I mean, that, for instance, the running coupling will go to infinity. And now, if you work it out, we know the running coupling now here. We know the lambda parameter from the fit of the previous slide. And now, if you compute the potential in momentum space, I mean, just this potential, and you are only interested in the behavior of the potential at very large distances, then this is a linear potential. It's linear in the distance between the quark and antiquark, and the factor in front is called the string tension. And the string tension, you know already, I mean, from redshift phenomenology, I mean, what the string tension is. It is about 440 MeV. The root of the string tension is about 440 MeV. And in this calculation here, putting in this relation, you get the string tension, and it turns out to be 2/3 over lambda squared. And if you put in the number from the fit, I mean, you get this value of 445 MeV, and the phenomenological value is 400 MeV. Yeah. So this is all consistent, and this gives you trust, I mean, in this whole machinery, I mean, of the gradient flow, which I will be using later on. And it also links, I mean, the running of the coupling, I mean, with confinement. And okay. Now it is interesting, I mean, to compare this beta function I've shown you, and you can also convert it, I mean, to the QQ bar scheme. And I do this only because I know I know the beta function to 4 loops. I mean, in the Q-bar scheme, this is this one. I also know the beta function to 20 loops in the Q-bar scheme, and this is from this paper here. And how can you do a calculation 20 loops? I mean, you can do it with stochastic perturbation theory. Probably you can even go higher than 20 loops, but that's what we have done so far. And you can see, I mean, that the perturbative beta function gradually approaches, I mean, the non-perturbative value, which is written here, which is of course should be a straight line here. Okay. Now I come to, with this preparation, I come now to the phase structure. And okay, so the interesting thing is, I mean, that or the most important thing, I mean, in this whole enterprise is that with increasing flow time, the gauge field ensemble, I mean, over 5,000 up to 5,000 configurations, I mean, they split into disconnected topological sectors of charge. And what I've shown here is the action. The action is basically the energy density times the volume. And I divided it by 8 pi squared. I mean, for a reason I will come back to in a moment. And what you can see is that this action, while it drops, well, this is a logarithmic scale, it drops very fast, and then splits into the different topological sectors. I mean, the lowest charge is charge 0 is here, and this is on the 32 to the 4 lattice. The charge 0 is down here, and the largest charge we have on this lattice is about 22, and this is here. And you can see that while this really splits, if this would, and they are really disconnected, yeah? Because the configurations always take the lowest action, and if it could jump from one charge sector to the other, then they would all end up here, but that is not the case. And what is the reason? I mean, usually, what in the continuum is very well known. I mean, in the continuum with very smooth fields, it's very well known that there's an infinite wall between the topological sectors. But we are on the lattice, and you can only jump from one charge sector to the other by a large ultraviolet fluctuation. And as this gradient flow is a kind of a smoothing procedure, this diffusion equation, then this cannot happen anymore. Yeah, but this is very important. And so the observables, I mean, in these various topological sectors, they can of course depend on the charge Q, and this is the reason, I mean, for later on, I mean, for non-trivial theta dependence, yeah, when we Fourier transform this from Q space, I mean, to theta space. This is also very important, I mean, for technical reasons. I mean, this means, I mean, that at non-vanishing flow time, I mean, the partition function or the path integral, I mean, which is the Young-Mills action plus this theta term here, that splits into disconnected topological sectors with this factor in front of it. And it doesn't matter, I mean, if you do a simulation, I mean, for instance, starting at theta equal to 0, then, I mean, you get these topological sectors. If you start a simulation, I mean, at a different value of theta, I mean, then you will get the same physics of the topological sectors, only the weighting, I mean, this weighting factor is different. So this is an important point because it allows you, well, because this is completely independent of theta. And once you know, I mean, the physics in these topological sectors, then I mean, you can compute the physics into as a function of theta. And this is, of course, only for the partition function, but usually, I mean, you have some, you multiply it with some operator. And so you, I mean, you can, this is describes, I mean, how you get to the theta value. Now, why did I divide it by 8 pi squared? I mean, you know that the volume times the energy density by 8 pi squared, I mean, in a semi-classical instanton configuration, this is just proportional to Q, which is just what you would write down for an instanton action. And for the larger charges, you can see, I mean, that they're really proportional to this Q value, but the ensemble average, I mean, really drops with 1 over the flow time, and so it does not stay constant. I mean, if it would stay constant, I mean, then that would be a dilute instanton gas, and that, of course, would not confine. Now, I will look now at 3 or 4 different quantities, and first of all, compute these quantities as a function of topological charge, and then I Fourier transform this to the theta vacuum and show you, I mean, how this depends on theta. So the first quantity to look at is the running alpha, and so if the general expectation is correct and the color fields are screened, I mean, for non-vanished theta, we should find in the very first place, I mean, that the running coupling constant is screened in the infrared. This means, I mean, if you have screening, I mean, then basically there should be no long range force anymore, and between any object, any color charges, and that would mean, I mean, that the charge or the coupling, I mean, should vanish. So I showed you before how you get the coupling from this energy density as a function of flow time and separated by Q, I mean, in the various topological sectors. And I call this now alpha, well, mu, of course, but also I distinguish between alpha and the various sectors. And that's what you get here on the 3 the volume. There's, of course, a volume dependence involved, but that is not so much of importance. What I've plotted here is the running coupling divided by the ensemble average as a function, the running coupling as a function of Q divided by the ensemble average. And you can see that it really splits off, and the charge go from 0 to the highest charge from bottom to top. I mean, here the highest charge, I mean, on the small lattice is about 6, and here it is goes from 0 to about 22. And okay. And what is interesting is, I mean, that for instance, I mean, if you were to take a configuration which charge 0, I mean, then it would really drop to 0, and there would be, of course, no coupling left. Now, as I said, I mean, we are interested in the dependence on theta, and I want to Fourier transform, I mean, the coupling, I mean, to the theta vacuum, and that is done in the following way. You compute the coupling, I mean, as a function of Q, then multiply by the phase factors, and then you have to multiply by the probability of finding a configuration of Q. And the larger the charges are, I mean, the smaller the probability is. So you have to know this probability factor. Yeah, but that is the easiest to compute. And you have to divide it, of course, by this partition function, and which is just this expression here. And when theta is 0, I mean the sum of p of q over all q value is 1. Okay, so this is my first result. I mean, again, for the 3 volumes, and what you see is look first at theta equal to 0. You see, I mean, what is plotted here is the running coupling, and the different colors, they label different values of t. And so what you see is that the coupling, I mean, at t equal to 0, I mean, it increases with t. Yeah, I mean, if you take this color into account. But what you see is also that at non-vanishing value of theta, the coupling does not go to infinity, and that would mean, I mean, going to infinity. I mean, if you have seen, if you have shown that is giving you infrared slavery and confining potential, but if the coupling stays finite, I mean, it does not give you confinement, but well, it's certainly not confinement. I mean, but something else. But I come back to it. But you can also see that at small flow time, I mean, in the perturbative region, I mean, the alpha does not depend. I mean, in the limit, I mean, of flow time 0, I mean, the alpha does not depend, I mean, on theta at all. Only at small virtualities or large flow time that it really explodes and gives you confinement. So from this, I mean, we conclude, I mean, that in the infrared, and you can see why why the gradient flow is so important, because I mean, you in the running coupling, I mean, this really runs, and you have to follow the theory over many scales in order to see this running. And so the conclusion, I mean, on this part is that the color charges are screened. I mean, for theta away from 0, and in the infrared, and that's where it counts. I mean, where the confinement comes about. Now it is tempting, I mean, to write down renormalization group equations. I mean, for the running alpha. This you can do by keeping, for instance, alpha constant and make a cut through here, or you can also keep theta constant and and look at how the alpha evolves. I mean, on this line, and that is what you get here, and what I plotted here is the inverse of the coupling, and it flows, I mean, from any value it can assume, I mean, at flow time 0. Now this is basically flow time 0, and this is flow time goes to infinity, and you can see, I mean, that the running coupling goes to 0. And the corresponding coupling renormalization group equation for small enough theta, I mean, are written here. I mean, for large theta, you have to express this by a cosine theta and this by a sine theta. Well, there has been. I don't want to. I don't have the time. I mean, to go into the correspondence with the quantum Hall effect. But the quantum Hall effect, I mean, this can be mimicked. I mean, by some kind of a sigma model, and where, for instance, the transverse conductivity is proportional to theta, which is proportional to the magnetic field, implying perpendicular to this plane, which is also CP violating, and the longitudinal conductivity can be described by some kind of a coupling. And what people have found, I mean, these authors here, I mean, that the running coupling also flows into multiples of 2 pi, 0 to pi, and so on and so forth. And this has played a certain role, I mean, in trying to understand, I mean, the strong CP problem. And people like Morozov, I mean, they have also tried to derive renormalization group equations on instanton physics, and they come to some similar conclusion.
Excuse
No,
me.
the next step. Sorry.
Yes, I have one question about previous slide.
Yep.
Yes. So here, on the left hand side, you show the running of the theta parameter as a dependence of theta on the log t. And can you derive this behavior in the usual perturbation theory, or it can be derived only?
No. You can you cannot.
It's
I
not,
mean, in perturbation.
Right? Yeah.
In perturbation theory, I mean, that is an interesting thing. I mean, in the perturbation theory, there is no CP violation. Yeah. Well, the CP violation comes about through instantons in the vacuum. Yeah. And the instantons are highly non-perturbative objects. Yeah. And they also have a certain size. Yeah. And so in perturbation theory, there is no CP violation, which which makes you think already, because I mean, in principle, if there's no CP violation at very short distances, yeah, then I mean, and there is a kind of a renormalization group transformation which takes you from small distances to large distances, and there is no phase transition in between or crossover or whatever. I mean, then you would expect, I mean, already on this level, you would expect that there is no CP violation. Yeah, I mean, there is here upstairs, there is no CP violation. I mean, alpha can take any value there. Yeah,
Mm-hmm.
Can take any value, and only when the instantons come into play and the physics of the different charge sectors, I mean, differ, and then I mean you get this kind of flow. I mean, there is some speculation. I mean, you might think, I mean, that this corresponds to an infrared fixed point, but while I have mixed feelings about the infrared fixed point, and you will see, I mean, why.
Okay, thank
you.
I
will quickly go now through the other observables. I mean, the next quantity I look at is the Polyakov loop, and the Polyakov loop, as I said, already describes the propagation of a single static quark, I mean, traveling around the periodic lattice. And I've shown here only the results for the, well, this is what I've shown here is the Polyakov loop squared. There's for various values of Q only on the 16⁴ lattice. And that the reason is that, I mean, if I would show, I also want to show how the Polyakov loop develops, I mean, with increasing float time, and if I would take a larger lattice, I mean, you wouldn't see anything because there are too many points. But let's look at this figure first. I mean, as I said, the Polyakov loop is squared. I mean, there are two Polyakov loops. I mean, and if there is okay, I mean, so what we want to see is, I mean, if there's any interaction between the static quarks, I mean, they run parallel, if they attract each other, if there is some kind of an effect of a string tension, a long distance force, or not. That's why we look at the Polyakov loop. And what you see is that that again, I mean, the Polyakov loop squared, I mean, it depends on the charge Q. In this time, I mean, Q equal to 0 is here, and the largest charge 6 is about here. And what you also see is that at some flow time, I mean, the Polyakov loop populates, I mean, well, this is an SU3, and the Polyakov loop can kinematically lie in this triangle here, and it populates all region. But you can also see that, for instance, for large values of Q, this one here, these are the dark points. The Polyakov loop stays small, whereas for charge 0, I mean, it joins these edges here. This is only to show, I mean, that the Polyakov loop follows a similar pattern, namely that it is really dependent on Q, and when you do a Fourier transform, you get what you will see in the next slide. What is interesting to see is that the average Polyakov loop, I mean, is of course 0. I mean, if you take the average here, and this means, I mean, that the center symmetry is really fulfilled. Now here's the result for the Polyakov loop. As I said, you do the same kind of same kind of Fourier transform, and we are only interested we are interested in if there's any interaction or any screening, and that is why we compute the connected Polyakov loop. This means, I mean, if there's no interaction, then this should be 0, because then you can take the square, you can put a vacuum in between. You can square, you can write Polyakov loop, put in a vacuum in between in the Polyakov loop, and that is exactly what this is. And if there's no interaction, I mean, so there's only the vacuum between the two Polyakov loop, that should be 0. So again, I show you the 3 different volumes, and what you find is very similar. But here, you have seen already that the Polyakov loop does not depend on the flow time, because it is renormalized and it is an observable. And well, we see some kind of small finite size effects, but you see that the Polyakov loop susceptibility here, I mean, well, it does not depend on the flow time, but it is certainly screened. I mean, there's no interaction between the Polyakov loops, I mean, at some value of theta anymore. That this does not shrink to 0. I mean, I will come back to that in a moment. Now, another quantity is the mass gap. The energy density, I mean, is a scalar quantity, and if you look at the correlation function between these energy densities, I mean, taken to 0 momentum, summed over all 3-dimensional space, then this projects onto a glue ball. Well, we are in the Young-Mills theory, where there are no quarks, and so this energy density projects onto the glue ball, and we subtract, I mean, the energy density average squared, and because we are only interested in the interaction, and while this multiplying this by appropriate volume factor, this takes the following form, namely the intermediate state is a chain of blue balls, and each has a mass of mn, and so the correlation function of this one is, well, I sum over t here, because I mean, I don't separate, I don't look at t value separately, because I don't know these quantities. I mean, I just know the average of the energy density. Yeah. And so this is the quantity here when you perform the sum and you approximate it by the lowest state, which is 0 plus glue ball in SU3, then you get this relation. This is a matrix element divided by the mass of the glue ball squared, and that is the correlation length. Yeah, I mean, okay. And the correlation length describes, I mean, the distance over which the color charges are correlated. Yeah. And so here is again, I mean, it's a very similar figure, I mean, to the Polyakov loop. And you see, I mean, that first of all, this quantity, this correlator does not depend on the flow time, and it is also screened. I mean, there is no interaction. This means, I mean, that the correlation length is basically 0. That at some value of theta, I mean, the correlation length is 0. This means there's no correlation between the energy density and these glue ball operators. And this also means, of course, that there's no mass gap. Now it comes a little bit technical. And if you want me to finish in time, maybe if you want me to skip it, I can skip it. But if you could stay on for a few more minutes, I mean, I will quickly go through the kurtosis, because this is relevant, I mean, to what I said at the beginning, I mean, to the conjecture of Cavendish-Gross, namely that the color charges produced by quarks and gluons, I mean, that they are screened by instantons. Yeah. So if you do not object, I mean, I will quickly go through that. And,
yeah, please include, yeah.
Okay.
Please cover this part. So, yeah, thank you.
Okay. So what we want to understand is, I mean, well, we have seen, I mean, that there's no confinement, I mean, at non-vanishing theta. The Polyakov loop is screened. I mean, there's no correlation length. And what about the topological charge? Yeah. And I've shown you already the result for the topological charge Q squared. But now I go one step higher and I take what is called the kurtosis, which involves the fourth power of the topological charge. And that is a very interesting quantity, because I mean, it can be written as this ratio of the free energy, and the free energy is just a log of the partition function. And okay, and this I plot here in this plot here. But what you should know, well, first of all, you see that when I take this, this is called the kurtosis, by the way, and this is plotted here. And what you see is, I mean, this is on a 32 to the 4 lattice, and because, I mean, the theory splits into topological sectors, and there's no interaction between the topological, no jump from one sector to the other. This quantity does not depend on the flow time, as for instance the topological accessibility, which I showed you at the beginning, also does not depend on the flow time. So if there's no interaction, for instance, between the topological charge, then you can do the same what I did before. I mean, this fourth power of this charge minus the average, you can divide into 2 squares and put in the lowest. Well, everything is positive here. Yeah, I mean, of this part here, everything is positive, as you can see. It only involves powers here. And so if I divide it into q squared times q squared and put the vacuum in between, which is the lowest state you can you can have, then this would be 1 minus 3 is minus 2. So the lowest value this kurtosis can take is minus 2. And so that is what you see here. You see that the kurtosis, drops very quickly to some number minus 2, and it starts to oscillate. This is due to the reason that we have only a limited number of charges, in our Fourier transform, and I will come back to that. And this oscillation, of course, amplifies, the higher powers in the charge. You look at the higher powers of the operators you look at. Yeah. But from this, well, it never goes larger than minus 2. So we can assume that this really takes the value minus 2. And this, as I said, this can be written, well, it should be known from continuum physics. This can be written as the fourth derivative of the free energy over the second derivative of the free energy squared. And if you assume that this takes a value minus 2, then you can, this is an elliptic differential equation of the second derivative. Yeah. So this is the second derivative of the second derivative divided by the second derivative squared. So this is an elliptic equation of the second derivative of the free energy, and which you can solve. And the solution, well, the second derivative is nothing else than the topological successibility at theta. And of course, this assumes this will be a minus 2 only, away from theta equal to 0. And this can be solved. This elliptic integral equation can be solved mathematically, and what you get is that this is just 1 over the volume times Weierstrass P function, and it involves one parameter only, no volume dependence, nothing. It's only a function of theta, no further volume dependence. And this parameter G3 is to make this periodic in theta. This is it's a very small number, but which makes this periodic in theta, which is the boundary condition. And so what do we conclude from there? What we conclude, that the topological successibility, if this persists for larger volumes, as I said, this the largest volume I have is 32 to the 4, and this volume dependence comes in, of course, through this volume dependence here of the free energy of the log theta. If you in the dilute instanton gas, this theta is e to the minus the topological successibility over 2 times 1 minus cosine theta. Yeah, and this means the log it would be the topological successibility times 1 minus cosine theta. But it is not compatible with the dilute instanton gas, because the kurtosis is negative, whereas in the dilute instanton gas also the Gaussian dilute instanton gas it would be positive here, and even for a Gaussian distribution it would be 0, and there's a clear deviation from that. Anyway, to conclude, what you find is that the topological successibility, when the volume increases, that really goes to 0, and the topological successibility is just this one without the square here. It's just without the square here, and this means, that the topological charge is screened, yeah, or the instantons are screened. And if you go back to what I said at the beginning of Cavendish and Rose, where they said that the color charges are screened by instantons, you can also reverse the whole thing and say that the instantons are screened by color charges, and that is probably what happens here. So it is, to some extent, I mean, it is the kind of a explanation. I mean, that what Cavendish and Gross conjectured, I mean, that is basically correct. So what I didn't tell you, I mean, is the errors, and the errors, I mean, they have various sources. First of all, there's a convergence of the Fourier series, and you need, in particular, you need this, the larger theta is, you're more precise, you need the probability distribution for large charges, and that you can, of course, increase. I mean, the precision you can increase by the statistics. But on the final volume, I mean, the topological charges generally limit to some maximal value, which depends on proportion to the root of the volume. And this means, I mean, in the Fourier series, you have only a limited number of factors here. With the maximum value is this true max, and so for larger values of theta, I mean, it will start to oscillate with the frequency which is given by this maximal value, and that is exactly what you see here. I mean, you can see, I mean, that and this was on the 32 to the 4 lattice, and if you look at the frequency, it is basically 22 in the right with the right factors, and one could do the same thing, I mean, for the smaller lattice, and so there are various ways of filtering this Qmax business, but well, I mean, we just do a fit, and you can see, I mean, this is a blue curve here, and but there are very other ways of doing it. But this is only to show you, I mean, that we have the errors basically under control. Yeah, and our 5,000 configurations are sufficient, I mean, to really draw these conclusions. Now, there's you might ask, I mean, how does this conflict, I mean, with the dipole moment? And on the lattice, I mean, there are various groups, I mean, computing the electric dipole moment of the neutron, including myself. And the latest result, I mean, is shown here. The dipole moment is given by some kind of a form factor, by a dipole form factor at 0 momentum transfer divided by the nuclear mass. And this is done, this is a plot of this form factor here, and you extrapolate to 0, and you can see that this is basically 0, and it's compatible with compatible with 0 within the errors. And so that is also what you would expect for the dipole moment to be. I mean, if this exercise is, I've shown you, I mean, the solution of the CP problem is correct. The other question is the axion. I mean, this is if you look at it, I mean, there are probably 30,000 papers, I mean, on the axion, and in this Patrick-Quinn solution of the strong CP problem, what one does is, I mean, that this theta term is augmented by the axion interaction. This means, I mean, this theta term, one adds an axion interaction, which looks like this. And this has a kind of shift symmetry. And so by employing, I mean, this U1 Patrick-Quinn, this anomalous chiral transformation on the theta vacuum, you can shift it into this axion business, This one here is CP violating, and this one is a pseudoscalar. It's not CP. They're both the pseudoscalars. They're not. It's not CP violating. So you can basically transform the CPU violation into CP conserving. But as I've shown you, I mean, the vacuum is unstable. I mean, you cannot just do it. The vacuum is unstable against this Petri-Quint symmetry, because I mean, at theta equal to 0, I mean, there's confinement, and if you shift it to theta not 0, I mean, then of course, I mean, you lose confinement, and so the vacuum is not invariant under this Petri-Quint symmetry, and so this is not a viable solution of the strong CP problem. So I'm basically done, and let me conclude. I hope I convinced you that the gradient flow, even though I could not, well, I could not go into great detail, I mean, what the gradient flow does, but if you want to, and you're not working on the lattice, the gradient flow, you find the gradient flow almost everywhere. I mean, and where you want to do renormalization group transformations. And I hope I convince you that this is a very powerful tool. I mean, for tracing the gauge fields over successive length scales. I mean, from the perturbative to the confinement region. And a key point of our investigation was, I mean, that the path integral splits into disconnected topological sectors for larger flow times. And as I said, I mean, in the continuum, the topological sectors are separated already at any coupling. And so, I mean, the further you go to the continuum, the sooner the splitting will happen when you go when you increase the flow time. And of course, when we have done calculations on 3 different values, which gave us control over the errors of the simulation. So the novel result, I mean, for you to take home is, I mean, that the color charges are indeed screened for theta larger than 0 by non-perturbative effects. And that, of course, limits the vacuum angle to theta equal to 0 at microscopic distances. I mean, and in the confinement model, the confinement limit of QCD, and this rules out any strong CP problem at the hadronic level. Now, you have seen, I mean, that the screening, while it shrinks a little bit, the screening length shrinks a little bit. I mean, when you go to the larger volumes, I mean, how much it shrinks, it's not clear to me, but I look at it as a gradual process, and as I said already, well, most likely it is crossover, and the screening is only completed. I mean, once the vacuum has attained a sufficiently level of color electric charge density, and that seems to be the case for this on the volumes I looked at. I mean, at these values, and I also like to say, I mean, that this whole result, I mean, of the screening does not really come as a surprise anymore. And so what I've said at the beginning, I mean, that really seems to come true. Why did it take so long? I mean, to really address this problem, and the reason is, I mean, that one simply did not have the tools to address the problem. And I mean, the tools is that you really have to look at, well, you have to really isolate the long distance mode, I mean, and follow them over larger distances. And that is only what the gradient flow was good for. Now, coming back to the electric dipole moment, I mean, well, the dipole that was found to be zero by, and not only by our calculation, by many other people's work as well. And it was found to be zero, I mean, as expected. And but it should also be said that if this upper limit, I mean, people quote, I mean, in the literature, I mean, it comes from some estimate of the dipole moment. And if there is no dipole moment, if there's zero, I mean, you can also not give any upper limit, I mean, on theta from the experimental bound of I showed at the beginning. Now then, this non-trivial phase structure of QCD, and I assume that this will also happen to be the same, I mean, in QCD with fermions, I mean, has far-reaching consequences for anomalous chiral transformations. And as you have shown you, I mean, that, for instance, the anomalous Pacheco-Quinn transformation, I mean, which is realized by the shift symmetry, I mean, under which, leaves the, well, it's not, the vacuum is not invariant under this this transformation. And this is basically true for all anomalous transformations, because, I mean, because of the anomaly, I mean, all anomalous transformations, I mean, where they will generate some kind of a theta term, I mean, when, and that should not be possible. So that's all what I have to say, and I'm looking forward to your questions. Thank you very much.
Okay, thank you very much. Are there any questions?
Thank you very much for a very interesting talk. And first of all, when you do lattice calculation for this non-trivial topological charge, how do you choose this gauge field configuration on the lattice for different topological charge?
Well, the topological charge, well, the topological charge is given by this expression here, yeah. And
right.
well, and this is in the continuum, and it takes integer values. Yeah. Now you can compute. I mean, to compute the topological charge, there are various possibilities. Yeah. First of all, you can. Well, what you know is that this expression FF dual can be written as a total divergence. Yeah. Mm-hmm. Yeah. Of a gauge variant quantity. Yeah. Mm-hmm. And but it is a gauge variant quantity. So what you can do is, this is, for instance, what this is called also the geometric way of computing the lattice, the topological charge. And if this is a gauge variant quantity, of course, I mean this cannot be in the single gauge, I mean, on the lattice, because this is, if it would be in the single gauge, I mean, then you could, being it on a periodic lattice, you could integrate it away. Yeah. So what you can do, you can go into different gauges. I mean, for instance, a smooth gauge at each point, and you compute transition functions between these different gauges, which are not the same at where they overlap, and construct a fiber bundle, and from that, I mean, that would be the mathematically way, I mean, of computing the lattice, the topological chart. But that's not what we are doing. What we are doing on the lattice is you do the same thing as you do here. In order to get f squared, I mean at this is basically the action. You get it from a closed loop of these links here. You can also get FF dual by a closed loop, but this closed loop will also extend into the other two directions. Yeah, it is basically a closed loop in the let's say into 1-2 direction, and then it continues into the 3 and 4 direction. Yeah, similar like this. Yeah, and this once you compute these this loop, then you can do the same expansion as you do here with these link matrices, but to get corrections of order of discretization errors. But when you do the flow, when you go to non-vanishing flow times, I mean, these corrections go away very, very quickly. So you basically compute it from these loops on the lattice. Yeah. But I mentioned only the first part. I mean, because if you are more mathematically inclined, I mean that is maybe the more appealing solution to you. I mean, calculating it from fiber bundle. But you can also do another way of computing is with fermions. You know that there's the Atiyah-Singer index theorem. And if you have chiral fermions, then each topological charge has the equivalent number of zero modes, and you compute, for instance, the number of zero modes. Yeah, I mean that you can do. If you have a chiral Lagrangian, you can take the Hamiltonian and you compute the eigenvalues, and the number of left or right-handed eigenvalues gives you the topological charge, and that has also been pursued in the literature. Mm-hmm. But this is the cheapest way. I mean, computing it via this loop is the cheapest way, and you can be sure that that this is the right way because you get integers. Yeah, I mean that's what you expect. And if you are at very small flow times, I mean, or even at flow time 0, I mean, you would not get any integers. You get only integers, I mean, at of this procedure. I mean, if you go to flow time 1 or already maybe or 2, but very small flow times. Yeah.
And one more question about in the earlier slide, you mentioned that this partition function, etc., is analytic in theta parameter.
Yes, I mean, let me see. This one?
Yeah, I think this one was earlier, but you mentioned that is it shown by Bafa Witten? Well, I don't remember exactly, but
well, it is very well known.
So my question is that when you extract your conclusion, do you assume this analyticity in theta, or is it necessary for your conclusion?
Yeah, there is some there are some, well, okay, I mean, here it looks like, I mean, if you're on the finite lattice, I mean, basically I don't see any problem. But what could have happened is, I mean, that there is spontaneous symmetry breaking involved, and there is a paper by Witten, I mean, that this partition function is analytic in theta, yeah, and there's also work by Asciore and Aguaro and other people, I mean, who have addressed this question, yeah. I mean, as I said, I mean, yeah, I mean, but what I wanted to say is, I mean, you might think, well, the simulation I do, I mean, is at theta equal to 0, yeah, and then it splits into these things, and then I know, and okay, but once it splits into these sectors, I mean, whether you do a simulation, I mean, at non-vanishing theta, if you could do it, yeah, or you could even do a simulation at imaginary value of theta, which has also been done. I mean, I have also done some simulation because there the action is not complex anymore. You can do by Monte Carlo, you can importance sampling, you can compute the partition function, and then, I mean, you would have a sum over a real factor here, and but in these topological sectors, I mean, they are basically the same. Yeah? I mean, it is the path integral, I mean, constrained, I mean, to this topological sector. What will change is of course the weight of these sectors. Yeah, that's why I said, I mean, what you need is larger, high enough statistics, but you should also keep in mind, I mean, all what I said is, I mean, all these figures, I mean, you can see, I mean, that you're only interested in, basically, I mean, for the screening, I mean, at very small values of theta. And I mean, I think the mission for me, it wouldn't make any difference. I mean, it could, if you wish, I mean, if you think, I mean, there's this is not good enough, then I mean, there may be something happening, I mean, here at larger values of theta, but if there's a different phase, I mean, that's also fine with me. I mean, my main point is, I mean, that these color charges are screened, and if you go back to this idea of Toft, I mean, you can imagine, I mean, if you look at the paper of Toft, I mean, there are a lot of things can happen. Yeah, I mean, in this scenario, yeah. But this is, I should also say, in Toast pictures, I mean, the at intermediate, this is a picture at maybe at only valid at intermediate distances where the gauge fields are more or less abelian, but probably at very large flow times, I mean, they will be they cannot be abelian anymore. There will be something like something else, like Z3 or something like this. So I would not rule out, I mean, with very high confidence, I mean, that maybe something might happen here at theta equal to pi or something like that. So.
Okay, thank you. So if I have more questions later, then I will ask by email.
Well, if you want, I can. You can I can send you my talk and you can put it on your website if you wish. Yeah, I mean, if you have questions, please let me know. And well, you know how to contact me. Yeah.
Okay, any other questions from audience?
I have some very stupid questions.
Yeah.
So yeah, it's very interesting. So thanks for the talk. And I'm wondering, the consequence of this non-trivial phase is like you have like a kind of zero EDM for like baryons, right? And so including like mercury or everything, right?
Yeah.
So do you have some kind of a prediction? Is there any way that any experiment that also can check this like in the future?
Well, what way? Well, well, I said, I mean, there's well, the only signature I can imagine, I mean, the CP violation. Yeah.
Mm-hmm.
Yeah. And but there can also be other sources of CP violation. And for instance, there are well, the theta term here, the CP violation of the theta term, I mean, they are of flavor singlet. Yeah.
Yes.
Yeah, they are flavor singlet. Yeah. And any anomalous chiral transformation is a flavor singlet chiral transformation. Yeah.
Mm-hmm.
Because I mean, because because the anomaly, I mean, is a flavor singlet. Yeah. So I would say the model, I mean, like Patrick Quinn, I mean, that is, I mean, the CP violation, I mean, is a singlet CP violation. I mean, I would rule out, but there can be non-singlet CP violations which are not which can be from different sources. I mean, from physics beyond the standard model. Yeah.
Mm-hmm.
And they could, in principle, I mean, they could also give rise to CP, well, electric dipole moment. For instance, DESY, yeah, I mean, which has nothing to do with the anomalous chiral transformation. I mean, or even you will have CP violation, yeah, and you can also have CP violation. I mean, from CKM, yeah, yeah. I mean, but that is what you have to distinguish. I mean, these two kind of. I mean, usually people say that well, any singlet CP violation would renormalize the theta angle, yeah, and that is basically ruled out, yeah. But well, any other CP violation, yeah, I don't know. I mean, but you should. I told you. I mean, this is amazing. I mean, what the experimentalists have done. I told you. I mean that this dipole moment, the limit. I mean, is. I mean, you take two charges. I mean, if you two unit charges. I mean, and you blow up the nuclear to the size of the Earth, and then it is a micron. Yeah, the charge is just a micron away, and that they can measure these kind of things. I mean, it's unbelievable. Yeah, and but I mean, in Germany, they're trying to build a dedicated proton ring. I mean, to compute the CP violation of the proton, but if you look at the bound, I mean, DESY, I mean, is maybe 2 orders of magnitude below, yeah, and CKM is even below that, yeah, and Of course, there's also the ether decay. I mean, and to pi, and this can also be a source for CP, but there's also only upper bounds, but nobody has ever turned this into a bound. I mean, or into a theta angle. Yeah.
Okay, thank you very much.
Okay, if there is no more question, then let's end today's seminar. And thank you very much, Professor Gerrit.
Thank you very much.
Okay, thank you
Yeah,
for inviting me. Okay,
Mhm.
okay, bye then.
Bye bye.